Welcome, my name is Job de Haas. My colleague here, Jasper van Woudenberg, he'll be assisting me and making sure I don't get tangled in all the wires and stuff like here. My presentation is about side channel attacks and countermeasures in the context of embedded systems. I'm speaking here on behalf of a company called Riscure, which is a small test lab in the Netherlands. We are a company that's fully specialized in only doing this kind of work for a wide range of equipment. So we are founded into testing of smart cards, which is actually the world where the side channel analysis is the primary attack vector, as it were. What we do see in our business is that it's also spreading. We also do, for instance, a lot of set-top box testing now. And every product where you have security, you'll find that these attacks become more realistic. The question is only when does it become a real threat? In what cases? And that's something I want to explore in this presentation. At the same time, I understand that this is not an attack kind that's very well known within the audience of a Black Hat conference in general. So I do want to go over the basics of a side channel attack only briefly. So I won't be explaining fully what a side channel attack is, but I will be going over some of its aspects and maybe specifically of interest, demo some of these things for you, including countermeasures that you can even develop as a software developer and see what they can do for your system and how you may be able to protect a bit better against such attacks. So, I broke that story that I now briefly explained up in 3 parts. I'll be starting off with just exploring a little bit the embedded security. How does it work? What do we see today in the security of embedded systems? How does it progress? Secondly, I'll be talking about the side channels. So what is a side channel? Some may be familiar with it. Actually, there were a couple of talks this year about timing attacks, which is a form of side channel. I'll be showing you a little bit of different side channels that you could use for such attacks. And then thirdly, I'll show you a couple of, or in this case, specifically one kind of such an attack, a DPA attack on a DES implementation. And I'll talk a little bit about countermeasures against such attacks, how they work and what you can do. Especially if you're not into hardware and you have no ability to change your hardware, as is common when you have embedded systems. Okay, just a few examples of embedded systems with security. What do these devices have in common? They have in common that they, from the operator or the manufacturer or the distributor point of view, they operate in a hostile environment. So in this case, it's the owner. So the owner of a USB stick stores his information on there, but he doesn't want others to get to that when he loses his device, when the device gets stolen. So people now develop USB sticks with a fingerprint sensor on them. Well, you can imagine that might give some access control. But how do they solve that? Is the data really stored encrypted? If so, where's the key? Is the fingerprint itself a key, and how can that work? So these are questions that you can ask about such a device. So how is it done? Another example, mobile phones. Well, mobile phones, of course, have a security history in itself from the unlocking perspective, which is a financial loss for the operator. But in this case, this is a Nokia, which comes with NFC and a secure element, as it's called, or a smart card inside that communicates wirelessly. And it will be used for payments, maybe access control, all kinds of applications. You can buy these phones and do your own development. There's an SDK and you can get everything. But you can see again already the mix of security features and threats to such a device. I mentioned set-top boxes. Set-top boxes from a smart card angle, and I will be talking a bit about smart cards in this context because it's the world we come from. It may not always be a good analogy for you if you're not really familiar with that world. But yeah, if you have any questions about it, just ask me. I can try and explain it in a different form, maybe. In this case, set-top boxes, they operate quite often still in combination with the smart card. So you have a secure smart card, and the set-top box decodes the channel for you with the secrets from the smart card. What you now see is that they are also moving to boxes without a smart card. So again, where do you store your secrets? How can you prevent anyone from taking them? In this case, you as an owner are actually the threat. You know, you want to get the keys. You want to watch free TV. The operator of the box doesn't want that. So from his perspective, this thing is operating in a hostile environment, and he wants to protect against that. And then a whole different world, and actually a very advanced security level. If you compare the security level of an Xbox, well, even to your own PC, it's of a much higher quality. Why? People don't want you to copy the games. You pay very little for this advanced machine, but you have to pay for the games to make up for that difference in price. So they put a lot of effort and security into such a machine to make it impossible for you, or at least very hard, to gain access to free games. So all these systems implement the same basic components. And the question is, how do they achieve their higher security level? So these are the typical trends that we see in that. Typical trends over the years, and we've seen a lot of these hardware reversing presentations of, well, you break it open, you start looking at the interfaces, you'll find debug interfaces, you'll find memory components, you'll find buses that communicate with sensitive information. And all those things are useful. You've seen it from those presentations, how useful they can be. So the manufacturers are just doing that. They're taking that away from you. They're removing the debug interfaces, blowing fuses, making keys that protect them. They protect their buses by scrambling. Doesn't have to be really advanced, but it's already quite a big step from just being able to read out a flash chip to be breaking scrambling algorithms that are on the bus in real time. A very important step is the increase in code integrity. Signing code before you can run it is becoming a norm in a lot of chipsets. Whether you're looking at, again, the pay TV industry or the mobile phones, they all now come with RSA signature verification in bootloaders, preventing you to run any code. I think even now the iPhone also is using this, for example. So these are clear trends that you're seeing across the purpose of the chip. So it doesn't matter where you're using it, people are implementing such features everywhere. And the objectives are clear. So the first thing is you do want to prevent running any unauthorized code, because if you can do that from like loading it through the bootloader, then you own pretty much everything in the device. How are you going to protect your secret keys if someone can run code from the highest level from the start? So that's what you want to prevent. And then the second thing is you want to prevent access to your confidential information. So you want to encrypt it somehow, which needs a key, which needs to be stored somewhere that you can't get to. If you look at chipsets that implement all these features and build a system with that, and you at least do the design proper, you actually end up with a system that's pretty well protected against what I would call like the conventional attacks. The attacks that you can do with a couple of $100 in equipment, like scraping off glue, soldering iron, flash chip reader, those kinds of attacks. Well, a little graphic. Let me get my coffee because it's getting cold. So, This is the first step that you do. Attach to a serial port, to JTAG, whatever, and pretty much control the device as a developer. What more could you want? If you are a developer, you pretty much want to be able to do everything on your device, so an attacker can too. So we take that away. You attack the flash. Why? Because it's a static device. You can take it off and read it at your leisure. So if there's anything worthwhile in there, like the firmware or secrets, whatever, you can just take your time and decode it. So people protect that by putting on BGA chips, glue, sometimes even crypto to protect access to the flash chip itself. So then we move on. We move on to the DRAM, which is still a bit harder. A DRAM chip is running at a couple of hundred megahertz. So if you want to sniff what's on the bus there, you already need pretty advanced equipment. But it can be done. We have done this in assignments, and it's possible to sniff what's going on the DRAM bus. So you can do this, similar attacks. What you also have is that the traces on a PCB, for instance, are still the same paths that you would access on the chip itself. So people tend to smear glue everywhere, put traces in the middle layers of a PCB, things like that, to make it really hard. Okay, is it really hard? Well, it doesn't really have to be. It's more difficult, but it's not hard. These pictures were taken from a site doing in the phone unlocking business. So these days, the mobile phone manufacturers have turned to the same kinds of protections, making it in chips that are glued to the board, that are difficult to replace, but they can be replaced. People just practice, and you can do this with just a couple of bucks of equipment. This is not expensive BGA equipment with XY tables and stuff like that. It's just by hand, and you can re-ball, and we use the same techniques also, because it's easy, it's cheap, and it's fast. Glue is the same thing. If you put glue somewhere, you can heat it. Joe Grant had a presentation on this with a lot of details also. And this is not something that's going to stop someone that is needing one attack to get the secrets and then can scale it up outside of this. What it does block is modifications of every box. So if you need to do this for every box, then it does stop the attack to a certain extent. It means that if you want to have free TV or something, you need to bring your box to a service point for some people to do this for you, because you can't do this at home, at least not my neighbors. And so that's the whole thing. But actually, this is what's happening in phone unlocking. This is when you bring your phone to get unlocked. They have shops, and this is just what they do. They just swap a chip on there, reprogram it, and it's unlocked. Okay, so a little comparison again towards the smart cards. So what I'm saying is that what I'm seeing now is that the chipsets are slowly moving to a level where they are incorporating things that we've seen in smart cards for a long time. It means that they're not using smart cards. So there are very few designs where they are now incorporating more smart cards. Mostly people are using things that they find in the smart card area and incorporating that in the more general purpose chipsets. Reasons for not using a smart card, it adds again to the complexity. If you've already got a very complex chip, why not make it a little bit more complex and just have it in one package? One issue is communicating with it. So I'm not sure if you're familiar with the card sharing attack in satellite business. If you've got a satellite set-top box and it's got a smart card, all the traffic from the satellite is going to the smart card and then descrambles the keys that are used for the video to descramble it. But how do you get them from the card to the box? Well, over the smart card interface. Now, these keys are only valid for about 10 seconds. So that wasn't much of an issue 15 years ago or 10 years ago. But now with the internet, you can just exchange those keys with your friends. And it's fast enough for them to use those keys to descramble their own video streams. So you see that it's an issue that you can't communicate securely with the smart card unless you're using a secure storage in your CPU again, which brings you basically back to the start. You're making your CPU more look like a smart card. Okay, so that's a little bit of the overview of how chipsets are moving and the security features that you can find in them. So now I move to the side channels. So, well, the basic theory of this is pretty simple. You have so-called, well, hidden or maybe undiscovered channels that equipment is emitting, and those channels may be sending confidential information or things that are related to confidential information. The question is, how do you get the confidential information, those secrets, out of those channels? And that's the theory and practice of side channel attacks. What are those channels? Well, you can have all kinds of them. Like I said, we heard today or yesterday about the timing attacks against databases. From very basic, that you can just have some commands that you make sleep, and then you just have a blind insert. Just you have to wait till the timing is over, and you can distinguish if the command was executed or not. To very specific, where you have in the database a B tree where there are splits in the nodes, very low level, but still sufficient in timing difference that you can distinguish what the database is doing. So what we are looking, and especially what we are looking here in a couple of demo setups I've here, is two things: is power consumption and is electromagnetic radiation. So we'll get to that later. So, does anyone know a sound side channel? Anyone an idea? In the back? No? Well, there was a nice research about typing. If you got a microphone in a room and you can listen into someone typing on a keyboard based on reflections against walls, for instance, and also the timing between your fingers on the keyboard, you can figure out what someone's typing. But another one that I read yesterday, because I was searching a little bit for examples, is a paper by Shamir, where he's listening really at a PC. So you just have a PC, it's running GPG or OpenSSL. In the meter or something, you put high-sensitive audio equipment, and you can actually measure instructions that are happening inside of the CPU of the running PC. So, and it's audio. This is not radiation or something like this. So all kinds of side channels can happen.
Was that audio stuff outside the PC or close to the CPU? You've got disk drives and all kinds of other stuff.
They did some experiments with close by and disabled the fans. And they did also experiments with more advanced equipment, I think 1 to 2 meters away. I'm not sure if they also disabled the fans, but they said also when you have very good audio equipment with good analog equalizers, you can also reduce the noise from such very specific noise sources. So probably you could see or hear something. Also in Cambridge, they do a lot of good work in this area, like looking at the ambient light from a display that's reflecting off the wall, and even try to see if you can still make up what's on the screen. So there are a lot of side channels that you don't realize. And actually, yesterday in the Johnny Long talk, just, social side channels, badges, stuff like that. There are so many side channels. In side channel analysis or attacks, we basically distinguish two types. One is the passive, where you just listen in. You just try to determine from the channels that are available to you if you can determine what's happening. The other one is active. Here you're actually using a side channel like a CPU is dependent on this clock. So if I can somehow fiddle with the clock of it, could I make it do something else that it doesn't expect, that the program doesn't expect, and it may have unpredictable results? Another is voltage. I today will be mainly or exclusively be talking about passive attacks. Well, a couple of simple examples. Timing attack. If a process is taking different time for two decisions, and I can measure the start and end, I can know the decision that was taken. That's the basic premise. Well, we've heard more things about this yesterday. The other one is power. So CPUs, and basically every electronic equipment these days is built up of gates. And gates switch. They switch between ones and zeros and back. And when they do that, they consume power. They consume power because they have leak currents. They consume power because they have to charge and discharge capacitors. Once a clock is switching, on that moment that the clock switches, all these gates become active. And they become active in a kind of an avalanche process until they're all done. And that's probably way before the next clock cycle even. And then on the next edge of the clock, or maybe the next up edge, they do their process again. And what you see is a profile like is drawn in the picture. You get a kind of spike at the start when every gate starts to be active, and then slowly it dies out. And the profile of that measurement actually says something about the number of gates that has been switching. And if your CPU is doing something related to a program or data, then that power profile will be related to that data. So the question is, how can you get the information out of there? The same thing you can do with electromagnetic field. Electromagnetic field is related to the power consumption. It's, the magnetic field is proportional. The electromagnetic field is a derivative of it. But what's important is that you can pick up that field with a coil. And that's something we've here in the setup. So you see, what you see in the image is a bit difficult to see because it's in like in an XY table, but I have it here in a smaller setup. So this thing is the probe, which is actually measuring the field and amplifying it. I forgot one thing. What's interesting about this field measurement is that it gives you something extra compared to the power measurement. While it's completely directly related to the power, the fact that you now are not tied to a wire going into your chip and coming back out, which is kind of one-dimensional, you now have a field in, well, actually 3 dimensions. Because you want to have a strong signal as possible, you generally want to be as close as possible to the CPU, but you still have the 2-dimensional layout of the chip to place your sensor and to have measurements that may be difficult to see on the 1-dimensional input-output of the power of the chip. So it might give you some edge on that field. Okay, so the question of getting from that signal to, well, your secret keys, basically. The first thing is the probe that I showed that you need. You can do it in power, measure current through a resistor. Then you need a scope. There's one here. It's a USB scope. It's a bit more expensive than the one shown yesterday. I'm not sure if you saw the talk about the wireless devices. This scope is about, I think, 1,500 euros, something like this. So it's a 200 megahertz megasample scope and a bandwidth about 100 megahertz. So that's what we will be using in the measurements. You may need an amplifier, depends on the signal that you're measuring. In this case, for the EM field, we definitely do one in this probe, which has been specifically made for this purpose. I'm not even sure if we have amplification in the power reader. And then in the end, you have a computer where you do all your processing. That's basically the hard work, because there you have to do all your mathematics, your statistics, to get the results. So I've got some test equipment here, which is a very advanced board. It's actually something called an Amstrad E3 mailer. And the cool thing about it is that it was, in the UK, it was, I think, £10 in the stores. It's a Linux board. It has a color LCD, a camera, a USB keyboard, a phone. And the trick was they were selling it because you had to dial into a fixed number. And that's the only thing that it could do. And so they were collecting the income from that. The reason I liked it is because it was having an OMAP processor, which is a predecessor to what's currently in a lot of the mobile phones these days. This is, so compared to the slow and unsecure version of what's in your mobile phone. And you can run Linux on it, so you can do your own development. We are actually not running Linux. We are just running a very small test program that can do a DES and an RSA. So the start was that we just first show what you can hear. If you just put something that you can listen with. So what it is, it's a normal hand scanner that you can tune. And what we do, we tune it to the clock frequency. So this is 150 megahertz. And then you just put it on AM or FM. And as an antenna, we use a very simple loop antenna, which is a bit of coax, and then you just have the core in a loop, and that's it. So, Jasper, my assistant.
I think I should put it on this microphone, maybe.
Probably, yeah. Oh, let's try that. So, let me plug in and plug out. So initially it's off.
Can you hook up this microphone?
It's live. Oh, okay. It's live. So, and this is just Linux booting. So this is what it sounds like if you boot Linux. So the point being that there's a lot of information there. You can already hear it. Apparently there's something that's related to what's happening inside. And everyone knows it because of your GSM going blah, 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 blah. It's the same kind of thing, but then in near field, which is very close to the chip. And it's very simple. Maybe we can also do the FM, because this was AM. Is it FM?
No, it's AM.
This is FM. Because I think it's actually going silent. Because in FM now you're tuning to 150, which is exactly the frequency there. So you just hear the variation of the clock. So anyway, just a quick demonstration to make it reasonably likable that there's information there that you might want to get out. So now we switch the setup. And I'll quickly explain what this is doing, because we need to boot up the test program again here. Whoops. Let me just put this here. So I'm now putting the probe, as it is shown there, directly above the CPU, while it's attached to a battery to reduce noise, and then again to the oscilloscope. What we also have is an external trigger, because when you're running something and it's running pretty fast, if you just hook on your oscilloscope and wait till it comes by, you won't see it. So you do want to do a very accurate triggering to find your program. So what I do now is switch to our tool. So this is a tool that we use in our company and also sell to do this kind of analysis. And it's kind of handy because it combines acquisition and analysis. So we can show just the acquisition part now. And what it will do is just, I think it just does 5 DES operations. Oh, it's still relatively visible. Maybe put it a bit better. See if the signal becomes. So, if you're a little bit familiar with DES, do you recognize something in this? Yes, the 16 rounds of the DES are clearly visible. So, well, again, that's another bit of proof that this is very likely to be usable in some form or another. So, yeah, good thing, yeah. So what can we do with it? What can we do with traces, measurements that we've taken? A trace is a word for a measurement for us. The first thing that you can do is start reverse engineering the information. If you see something like this and you see the rounds, it tells you something. But also, if you would do the same thing for the boot process, for instance, you could also maybe see what's happening in the boot process. Maybe you can identify where it's going over the memory. Maybe you can identify where it's making a signature. Maybe a decision on a signature, stuff like that. You can also zoom in and maybe find very detailed differences. In this case, the bottom trace shows you 2 traces that are almost similar. And what you'll see is that, well, the first part is practically similar, and then suddenly something happens there, and then it becomes actually similar again, but now shifted in time. So apparently there was some decision here where the first time it took longer, and the second time it was shorter. And actually what this was is a lookup table in a crypto algorithm where the table is 512 bytes. And this is an 8-bit processor. So what it's doing is it needs to look up this index, but it's only got 8 bits. So half of that single bit, that 9th bit, has been made into a decision whether to go for the left table or the right table or the up or the lower, or whatever. And that manifests itself as a time difference that you can see when you measure. And if you know that this is related to a key, you can just do a couple of measurements with certain input data and figure out what the key is. Okay, another form is differential analysis. So it's not always so easy that you get measurements that are so different that you can see the information visually in it. In this case, the traces are pretty equal. You don't really see a difference. Only when you take the difference, you start seeing information. In this case, apparently, at the 3rd peak, something happened that's related to, in this case, the input. Because between the 2 traces, input was varied, and apparently this is related to that input. It might, of course, also be noise, but then the trick is to just take more measurements with more random inputs to see which part of the information is actually related to the difference that you're measuring. And that's what's called differential power or EM analysis. Now, I'm not going to go into all the mathematical details of how you do a correlation, but you have to think statistics and the fact that you want to have a population with a lot of random inputs, for instance, where you can make at some point a distinction, reduce the noise and find the information in the input that's relevant for some part somewhere in the output or in the measurement. And if you make such a correlation, you get something like this, where every time there's a high value, it means that for that bit of information, there apparently was a correlation in the measurement. Now, these are bits from the input data. So we've put data into an algorithm, and every time a little bit different data, just random, and it can be a lot of data. So you can do like 1,000 measurements, 100,000 measurements, 1,000,000 measurements. Just sufficient to reduce the noise and make the correlation visible. And it doesn't have to be visible to the eye as long as your program can distinguish between the noise and the correlation. But these are very nice pictures. They are very clear, and it helps us to see what happened in this algorithm. And in this case, it's again a DES operation. And what you can see is that the input bits of the data for a DES are operated at different moments in the algorithm, which is correct if we look at a DES, but we'll get to that a bit later. Suffice to say that you can see that the bits are split into the left and the right half. So even and uneven are moving to two different times in the algorithm. And you can imagine that if you can do this with the key information, that you could also find the key. The only thing is you have no way to randomize the key. There's no point in being able to randomize the key. So you can't use this directly to find the key. For the input, you can use it directly. You can directly correlate your input with the measurements and find where it's used in the program. For the key, you have to figure out something else. And that's the differential power attack that I'll show after this. Just a short break back to secure CPUs. So what we're seeing is that instead of a CPU being dependent on external storage and crypto and software, CPUs are changing in that they are actually storing secret keys inside themselves. They are blown in there by fuses or programmed into OTP, and they have their own crypto engines to operate on them. So the secret key never has to leave the CPU, and it can be used to secure all the other parts of the chip. It can be used to securely enable or disable the debug interfaces. It can be used to authenticate to flash chips, for instance. So to attack such a system, the DES key, for instance, or the AES key in there becomes a very valuable property. So that's the thing that you would want to attack with a side channel attack. Notice that I also shown an external communication channel there. The question, of course, is always, what's the easiest attack? Is it easier to do a side channel than, for instance, try to break just the client application on the CPU? I think that now in the parallel session, there's a discussion on the iPhone that has been broken by a bug in the Safari browser. So they have all this code signing and maybe other security features, but they broke the CPU or access to the device by a mistake in the browser on it. Now that doesn't mean that you will maybe get access to the secret keys on there, because it might be a different privilege level, but it does show you that it's by far not always the most logical way to go for a side channel attack if there are so many other ways into a device. So it's only when all those other angles are closed that a side channel attack becomes relevant. Okay, on with demos. So let me think. Measurements. The thing we are now switching to is a smart card. Why? Because it's a very bad smart card, which makes it very easy, well, easy is a big word maybe, which makes it likely that we can do it in a live presentation. Normally you do have to take, a couple of thousand measurements maybe, which takes a couple of minutes to run, and then you need to do your analysis, so it all takes a little bit much time for such a presentation. However, with this card, we hope to do it in 500 measurements. So we'll now switch, and Jasper will set up and run the...
Want to get a key in there?
Oh yeah, good point. we actually had the opportunity to put a key in there by choice and see if we can break it. So, does anyone know 8 bytes? Well, he just started typing. DE? C0. Okay, 3 more. 8-3. Oh, I know it's the last session. Okay.
And one more, I think.
And one more?
7F.
Okay,
Gotcha.
let's go.
Okay. Yeah.
So now what the tool does, it just, damn, is it yellow?
Yeah, I tried this one already.
This is, I don't know. Ah. Okay. So what the tool does, it just runs, first it programs the key in the card, and then it just runs over sending random data, triggering the measurement, getting the measurement out, and then also getting the random reply, the encrypted reply back, and storing that with the trace. So every measurement has its own input and output data, so that we can then use it for the correlation attack. So, well, this will be measuring for 2 or 3 minutes, so I quickly go back to explain to you this attack.
Suppose in building the smart card you limit the number of times it can be used so that by the time we do this analysis, the smart card is probably not so good.
Yes. The question is, what if you do just limit the number of acquisitions that you can do, just the number of transactions? That's a way to limit the threat. If you know that your countermeasures are good enough that an attacker needs at least so many measurements, then this is a way to prevent it. And actually this has happened also not in a side channel attack, but in the GSM SIM cloning attack, where you have a weakness in the algorithm that if you do sufficient transactions on your GSM SIM, you can clone it. And then the GSM operators try to limit the number, but then the attackers thought of a better way, so they got under that limit. So, but limiting the amount of measurements you can do with certain key material is actually the key to limiting your exposure. So actually I was going to explain quickly, because I also need to keep track of the time. I've got a half an hour, right? Okay, so this is DES. Now, I'm not sure if everyone here is a crypto guru, so I just want to try and get across the main message, which is this. Like I said, input correlation is easy. You have the input, you have the measurement, you just correlate and you find the peaks where the input is used. With the key, you can't do that, because that's the secret. So what you want to do is you want to pre-compute to some point in the algorithm where you know the key is being used, but maybe just barely, and then try to correlate with that. Now, still that's not so easy, because you still have to go through a whole lot of keys. Well, luckily, if you look here in the DES, you have 2 halves, and then 1 half goes through the F in the first round. And the F function itself looks something like this. It's got a permutation, so if we're coming in from the input, we still haven't encountered any key, so we still know exactly what will be at the output of E. And then the key that we don't know gets mixed in, but then broken into pieces. So the 48-bit round key, which is only a part of the real key is 56 bits. So 48 of these have been taken here, and then broken into pieces of 6 bits. So suppose that we can now just start guessing 6 bits. That's a lot less. That's 64 guesses to find just that little part of the key. Because we XOR those 6 bits with the information we have from the E permutation, and then we put it through a lookup table. which is just a nonlinear combination of input and output, and you just get a value at the output that depends on the 6 bits of the key and the stuff that you put in before, which is random. So that's exactly what we're going to do. We're going to just guess for every subportion, for every S-box, we're going to guess 64 keys and see which one correlates the best with the measurements that I've taken. Actually, here it is again. So we actually simulate the DES all the way up to the point of the output of the S-box. And we calculate the output of the S-box for all the 64 keys that we can have for that subset, combined with our random input. And if we have sufficient random input going in there, then this will eventually give you a correlation that's very strong for the correct key and 0 for all the other keys, which looks something like this. So now we are probably not going to achieve this kind of level because this is a very nice peak, but we do hope to see something that relates to the key that we're looking for. And actually, going back, because for the first round we only get 48 bits of the key, because that's the first part that goes in. So to get the whole key, we need to do the second round also. But we know the first round key, and then we use that to break the second round key. Because then you can do all your calculations up to the second round, and then the guessing game starts again. Actually, so the measurement succeeded. Okay, well, Jasper, maybe you better explain.
So we've taken a couple of hundred measurements now, 500 to be exact. But one of the problems is with these kind of measurements that when we perform our statistics, we do it on sample columns. So we take one sample column of 500 traces and we run our statistics on that. But after these measurements, which are still pretty raw, we don't have the perfect alignment yet. So there's a little bit of jitter in the time. So the first thing we need to do is get all these traces aligned. I'll show you exactly what the problem is. If I zoom in a little bit on this trace, you can start seeing the clock cycles happening. Now this is a typical image of what we see. Like all the peaks that Job showed before in the slide is all the transistor switching, which goes down, and for each clock cycle you have a peak again. But if I overlap that with a second measurement, you'll see that there's misalignment. I can show you that visually by just grabbing one of the traces and aligning them manually. Like this is what we want to have, and this is what we have right now. Now, of course, we're not going to align them all manually. We have some more advanced stuff for that. So I'm just going to select one clock cycle and perform a pattern match with all the other traces.
That's too much.
Yeah, too much. What should I take?
It's 105.
Okay. Yeah. And this match will just align all the traces.
So this is just a pattern match. It's just searching around in every trace for something that looks a bit similar with a limit shift to the left and the right so that it doesn't go over the whole trace. And then at the bottom, well, it's just finding all those shifts. So this takes a little while.
Yeah, misschien de adapter. The adapter for this laptop. I don't want it to die.
Oh, power.
Power. Oh, it's already there. Excellent.
Okay. Yes. Yes, the measurement actually contains, I think, 3 rounds or something like that. Everything. And later, during the processing, you will recognize them more easily.
Yeah. So now I can show that what the effect is after alignment. We have the clock cycles again. And if I add one more, You can see they're more or less overlapping for all the traces. So the next step is, because this is a lot of data, each trace is about 400,000 samples, I think.
Yeah.
Which takes a lot of processing, which we don't want to bother you guys with. We're first going to compress each trace just by resampling. So we're actually going to represent every clock cycle by one sample.
So what happens is that what we say is actually what happens in the clock cycle is we just average it out, because the average value of it we think is related enough to the input to find our correlation. So we're not interested in every subsection of that clock cycle. We just throw the whole clock cycle in one bin and make it one big integer, or float in this case, and use that to do the correlation with. Now, in this case that works. Of course, it may depend on the hardware that there may be a very special spot in that clock cycle that's very sensitive to the input data. Then you don't want to do this. You maybe just want to take that piece of the clock cycle. So it very much depends on the implementation. This is more or less the quick and dirty way. You just throw everything together. It is important that you have everything properly aligned. So if you would do this without the alignment, you get that you're comparing a lot of things that you shouldn't compare. And actually that introduces noise in your correlation. Okay, so now you see the above picture, which has been downsampled. So again, you already now see much more structure. And actually now we are not going to show you all the way how you would find the S-box, but we know where it starts and ends. So what we're now going to do is first make sure that this, again, is properly aligned. Because the clock cycle alignment was not sufficient to align them all. What you'll see is that there's a slight difference between each one in the structure of where the S-box was calculated. So we just want to align all the S-boxes nicely on top of each other.
Okay.
So that was this. So that goes a lot faster because a lot less data now. And now we're ready to do the correlation. So now we are going to select the area where we know the S-box is being calculated. And we use, in this case, the routines that are used for the correlation part. In this case, we're using the Hamming weight. So the Hamming weight of the output of the S-box. Because all the transistors are switching at the same time, and the output is used as like a nibble or something in a byte, we get a Hamming weight effect that it matters on how many bits are switched to 1 and 0. And that's what we use to correlate. So now the correlation runs. And what we'll see is now all kinds of traces. Those are the key guesses for each S-box. And then at the bottom, I'm not sure if this is readable. It's a bit small. You'll see some calculations that have been done on those traces. So all the top 4 best correlating traces have been selected. And you can already see that for the last S-box that the top correlation is almost a half. And then the second one is 0.34. So there's a clear difference between the correlation between those S-boxes. So probably the one that's selected there is the correct one.
Next.
Do we want to check if they're all this good?
Yeah, we can
Then
see.
we can already predict if we will fail.
7 is okay. That's good.
okay.
Good. That one's a bit shaky. Number 3.
Yeah. Okay,
This one is
so
also.
this is the first round key. Now we're going to do the second round key. Yes.
Do you guys end up knowing what all those rounds just look like visually, so you can just select those? And that's just
No, not always, because you do see the structure, but then it's still a question which part is which part. But if you do the input correlation first, you'll see where the input bits are used last. So that's where they must go into the S-box, apparently. So that gives you the start. It's done?
Yeah.
Okay, so it has found DE, BC, and it was supposed to be
Dead.
okay, so that's a mismatch. Oh, actually, it has 2-bit mismatch. So it already knows, because there's 84 bits in the first round key and 84 bit in the second, that you have a lot of double bits that should match up. So this complains if there are bits that don't match up from the first round and the second round. So we definitely know there's a mistake in this key, but it's also very small. There are only 2 bits. So you will have to brute force those two to find the real key. Still, the key doesn't look much like the key that we put in. Anyone know why there's more difference than just those 2 bits?
Because the round keys are all different.
No. There's, the last key is the real key that's been reconstructed from the round keys. But in DES, there's only 56 bits in a key. And we entered bytes. 8 bytes is 64 bits. Because the parity bit is not used, so the program can't deduce what the parity bit was. So it puts it on 0 for all the bytes. So that's why you lose all the bit 1 in the key. So the last one is 7E. That's a good guess, because we put in 7F. So this is basic the principle of breaking a DES key. Anyone got any questions on this part?
You always add that parity bit back in to 1, or is that?
No, because if you just put them in as bytes, like a key, it's also not a parity bit, right? If you just put in hex data, it's just lost. The parity bit generally is not used anymore in DES. So.
How fast is this process for running a cache?
The smart card, you mean? It's running at 4 megahertz and 3 clock cycles per instruction. Okay. Then I'll move over to countermeasures. So what do you want to do with your countermeasures to prevent something like this? Well, there are 2 things. You want to decrease the leakage. Now, like I said, I was assuming that we have no control over the hardware, so we have to do something else to decrease leakage. One thing is to balance values. Like I said, we use the model of a Hamming weight. So if you make sure that all your Hamming weights in your processing are always equal, maybe you'll leak less. One way is also to limit the number of operations per key, so the limit on the transactions, but maybe also a protocol change. The other thing is to increase noise. Now, again, we just don't have the capability to add a hardware noise generator to our embedded system if it's in the CPU. But we can change timing. All the correlation depends on that everything is happening at the same time, at the same column in our measurement. I mean, it doesn't have to be at the measurement time, but at least we need to be able to shift it back into the same column for it to work in a correlation. So if we can make the timing very noisy, that would help. There are basically 2 concepts that you have in doing this in passive side channel. One is hiding. Hiding is a concept that you try to make it difficult for the attacker to know when a certain value is being processed. So you don't really change the fact that you have to process this value in your program, but you do make it difficult for the attacker to find when. And the other one is called masking or blinding. And with this type of countermeasure, you're trying to change the values that you are processing in your program without the attacker being able to know what you're processing. Basically, what you do is you mix in a random value in your algorithm and use that throughout, somehow masking the real operations that you're doing. At the end, being able to reverse the effect and extract your real output that you're looking for. So basically, you can see it like this. You have an algorithmic value, like, okay, I'm doing a DES with this key, then I have to do this kind of operation. By changing the algorithm by using a random value, for instance, to mask it in, you change the value that the actual XOR instruction is processing. So the power consumption is also related to that new process value, making it difficult for an attacker to know. And then you hide it. You try to make it very difficult for an attacker to know when this value is being processed. Going a little step back, actually, you can already do a lot by just changing your protocol. I've taken here a picture from a paper by Paul Kocher, and it's about using a key in a way that it's actually being used only once. So you start out with a key, and in this case, you do have to have a server that knows at what stage you are in your transaction. So there needs to be some kind of synchronous system so that both sides know at what stage in the transaction they are to know how to process and generate a new key. But if your SHA operation is leaking, then you'll never leak more than 2 SHA operations. And if that's only a couple of bits per SHA operation that you're leaking, then you'll never leak the complete key. So this is a way to prevent leakage. Well, now I just have more or less a random bag of examples. Let me check the time because I also want to give a demo. So I'll go over this a little bit quickly. Well, first of all, time dependency. You do want to remove time dependency. That's going back again to the timing attacks. And that's not only the instruction timing, but also the fact that you do conditional branches on things that are determined by key material. A very simple one is inserting random knobs. You know, if you just start inserting random knobs, for an attacker, as long as he can't distinguish those knobs from other instructions, or can recognize the parts he's interested in, you can confuse an attacker and make it more difficult. You'll definitely need to take more measurements to get the same amount of information out of each position in time. Another one is changing order. So if you've got multiple operations that need to be done that don't depend on each other, you can move them around. Like S-boxes, generally everyone goes through S-box 0, 1, 2, 3, 4, 5, 6, 7. But it isn't necessary. You can calculate them in any order. If you do that, you reduce the chance for an attacker because he has to take many more traces to get the same amount of correlation for each S-box position. It goes something like, if you've got 8 S-boxes, your correlation, to get the same correlation, you need 8 times 8 more traces. So 64 times more traces. It goes by the square. So that's significant. So if you take 100,000 traces and you have to take 6.4 million, that's a significant difference. Because we do these measurements, and sometimes they take like 4 or 5 days for a measurement set, and only then you can start processing to find out that you did it wrong or something like that. So it can be quite an obstacle. Well, and then of course you can implement a masked version or blinding, and RSA that's particularly well known. Actually, in OpenSSL currently also has a blinded RSA. Against timing attacks. Okay, more demos. So we go back to the DES measurement on the OMAP board. And what I'll show is the effect of inserting some random information in there. So what we have here is a DES, and it's always operating with the same input data. So it's not changing or random input. So this is always the same input without any countermeasure. So if you scroll through these, you'll see that there's almost no difference. They line up nicely. So also here the sidechannel attack works really well. I didn't do it live because it takes a little more measurements, like 20,000. but it works. So now we have a version that inserts randoms, all places through the DES operation, and still with the same input data. So there's no difference. It's not any variation you see is not from the input data and not from the key. So you can already see in the measurement below that it's, I'm not sure how many is it taking?
100.
Better not go through all the 100. So if you scroll through this, you already see that it will shift in time, it will shift in amplitude, purely from introducing some random knobs in this algorithm. And this will take significantly more measurements to break. Okay, another example is RSA. A very basic RSA implementation. So we move the probe. For some reason, the RSA is better visible on another part of the chip. I don't know why. Maybe it's also not when you do a DPA, but for the SPA that we now do, it's much better. So this is only taking one measurement. And, well, let's see what we find. We do a little bit of low pass filtering on this one to make it more visible. Yay. Okay, so what do we see? Are you familiar with RSA implementations? Well, what you do in an RSA is an exponentiation. And for each bit in the exponent, you do a square operation. And if the bit is 1, you do an additional multiply. And what we see here is you see each peak downwards is the boundary between a square or a multiply. And then where that dark bit is, that's the multiply operation. So I don't have a pointer, but oh yeah, better just do it that way. That's easier.
This one.
So what we have here is a square, 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 multiply. So what does it mean? That means a 0 bit, a 0 bit, a 0 bit, a 1 bit, a 1 bit, a 1 bit, a 0 bit, a 1 bit. So that's the secret exponent of RSA that you see there. Now this is a well-known issue with RSA if you implement it very straightforward. So a simple countermeasure against this SPA, and I do want to say this is not the best countermeasure, is to do a so-called bit group-wise implementation. If you do a little mathematics, you can make it clear that you can do pre-compute a couple of multipliers, and then what you do is a square multiply with a pre-computed multiplier, but then for every bit group. And that means that it's a constant. You get square multiply, square multiply, irrespective if the bits of the exponent are 0, 0, 0, 1, 1, 0, or 1, 1. And because you can't see the difference between the multipliers, you don't visually see any difference anymore. So that's what we see here. Now it's all the same. Well, probably you didn't remember, but down here at the bottom, you see the result of the encryption. And it's the same answer as the previous one. So the algorithm didn't change, the input didn't change, and the result didn't change. But you do see that visually, there's now no noticeable difference anymore. Now, that doesn't mean that this is secure against a timing attack. For a timing attack, this does nothing. So there are countermeasures for different reasons, and you probably should combine them to make a secure implementations. Let me quickly switch. Well, this is what I was explaining, so I won't go. This is off. Has the slide been this crooked all the time? I'm not sure if this... Oh well, sorry about that. This was the implementation that is simple, and this is the bit group, but I don't want to go too deep in this kind of mathematics. Another implementation in this measure is blinding. It's a kind of masking on RSA. The way you do that is, in this case, you change your message, your input message, by multiplying it with a random value, and then perform the RSA on that value. So now what you get is that the time doesn't depend anymore on message C that you put in, but on something you don't know, something that's been multiplied by a random. So your timing attack will fail. And at the end, you just divide the random out of the equation again, and you get your encrypted message, or decrypted message, in this case decrypted, in a way that you can't determine timing of this algorithm. Now, there are also ways to do this with the exponent, which again helps with the SPA attack, for instance. Okay. Yes, I'm winding down. So these were a couple of examples. What you see here, and actually the examples you've seen here, I made them only today. I was a bit late. And I already this morning ran into troubles because my SPA didn't work. I couldn't see it. The implementation that I had originally for the RSA already didn't have a real SPA. There was a difference between the multiply and the square, but it was only something like 10 microseconds on 400. So you didn't even visually see it. So I had to modify my program and put in a lot of garbage to make it like a big difference so that you could now see on the screen that there was a square and a multiply. So what does it mean? That means that when you're doing some things in software, you basically have no idea what's happening on the device. You have to measure and to verify what's actually happening. And it goes for inserting vulnerabilities, like I was doing this morning, but it also goes for fixing vulnerabilities. So if you're concerned for something like this, you do have to do your own measurements, or you have to have someone look at it to know what's happening. Actually, in the banking business, for instance, there's a lot of certification in this area. Bank cards are certified. FIPS 140-3 is just out. Actually now also for certain levels requires that you do a side-channel analysis. So it's a way to verify that you're doing the right thing. I've been talking a lot about countermeasures, and one thing to note about this, and maybe it's a little bit peculiar because you don't see this much in the wider area in the security space, but countermeasures and even the attacks in this area have been patented by CRI, a San Francisco company, which is actually founded by the more or less discoverer, or at least publisher of these attacks in the mid-90s. So if you're implementing or want to have countermeasures in your systems concerning this, then it's good to check with them, because they do have implementations already for this. They looked into them, but also licensing issues may be involved there. So they have a lot of patents on their website that have useful information, like the protocol that I showed, more of those, and also about blinding RSA, for instance. And then it's time to wrap up. Well, my main conclusions is that with the increase of security features in embedded systems, the side-channel attack will gain in importance and will be maybe one of the more likely attack paths compared to, well, the more manual work that we've seen in the past. A lot of these chipsets do not yet contain specific countermeasures against such attacks. Even companies making smart cards and more complex chips, smart cards with a lot of advanced countermeasures, do not put countermeasures in the chipsets that you'll find in set-top boxes or mobile phones or whatever. So if you're developing for that, take that in mind. Well, we've shown that it works, so it is a threat. But when you have, as a software developer, are aware of ways to implement your countermeasures, you can make it a lot more difficult for attackers to actually do them on your device. And basically that ends my presentation. Any questions? Yeah, all the way in the back. That's a good question. How much faster does the sample rate need to be than the clock frequency of the chip? That really depends, but it doesn't need to be faster, actually. So in this case, we're sampling with 200 mega samples, but only 100 megahertz bandwidth, a chip that's running at 150 megahertz. We've even seen cases where, for instance, the RSA operation in software on a 300 megahertz or 200 megahertz system actually is only running at a couple of kilohertz with the multiply and square operations. So if you can see them, you can even find them at a much lower frequency. So the frequency that the operation that operates with the secret key is at can be much lower than the chipset frequency. But for smart cards, where we do with a lot of countermeasures, with high-level attacks, we can easily be at, we have scopes going to 10 gigasamples for things that only run at 10 megahertz and still get information from that. So you do want to be faster if you can be faster.
Are there a lot of vulnerable, naive RSA implementations out there?
Yes. Yes, almost everyone that just starts out does it wrong. That's basically, OpenSSL even had a blinded RSA, I think, that was not good. So even after they did the blinding, there was still a timing attack. So there's always countermeasures that make it more difficult, and countermeasures that make it, more or less impossible. In general, the countermeasures that make it a bit harder are the ones that aren't even implemented. So those are the ones that should be implemented at least.
What about looking at hardware applications?
In hardware, there is a difference because hardware often does a lot of things in parallel. So, for instance, the S-boxes, they will be calculated at once. However, the leakage still is proportional, to all those 6 or 8 S-boxes. Only the leakage is less, so you need to make more measurements. Also, it's faster, so you need faster sampling times. So that's also an important factor there. What we see is that also that hardware countermeasures are often really, really effective already. So in the chipset, in the smart card business, it's already a big fight against only hardware countermeasures. So they could have fully, simple, straightforward implementation in there, and just the hardware countermeasures around it are so difficult already that it becomes much, much harder than something like this. All the way in the back? Okay, so the trade-off between the countermeasure and how it impacts the performance. Well, there definitely is that impact. So it's always a choice by the manufacturers in how much they weigh that. And also, often they are all full configurable by the developers. So you still have influence as a developer how you want to do it. For instance, they also have like noise or full power only for the crypto operation and turn it off again. Things like that to balance it out. I've no time left, so you have to come up to me and ask me directly. Thank you.